Okay, welcome everyone to our latest webinar where we're going to talk about how viscosity measurements are not just a single point and that you can go beyond the single point and get much more information that could be very relevant to your systems. So when we announced the webinar, we sort of highlighted the fact that we're going to talk about the importance of temperature dependence on your viscosity. And that's going to be a big part of our discussion today, but we're also going to add a little more that sort of came about naturally as we were collecting the data. So let's first just review to get everyone reminded about what viscosity is and what it's telling us. So viscosity is just generally used to characterize the resistance to flow, so the resistance a fluid has to deformation. And viscosity is not a directly measured property, it's calculated. So it's defined as the shear stress over the shear rate. So if we look at our schematic here, where we have a fluid between two plates, and you can imagine you want to deform this fluid, induce flow. So you're going to move the upper plate at a particular velocity, and our fluid is contained within this region with a gap h. And depending on the resistance of the fluid to the flow, it's going to require a particular force. And so to calculate the viscosity, we're just looking at the force required per unit area, the area being the area that's in contact with the fluid, divided by the shear rate, which is in this particular geometry just defined as the velocity divided by the gap. So this is the simple definition of viscosity and how it is calculated. And although viscosity is a macroscopic property, it's going to reflect what is occurring on a microscopic scale or molecular level. So what I mean by that is you have particular components in your fluid and they have a particular size, shape, and interact with each other in a given way. And because of these interactions, then you will induce a microstructure within your fluid. And so the viscosity or the resistance to flow is going to depend on all of these molecular scale properties. And simple fluids, so by simple I mean solvents or your buffer formulation, will have simple behaviors. So for example, as I mentioned, we're going to address temperature dependence of some systems. And for the simple systems, generally you have temperature dependence that follows the Arrhenius law. So the viscosity will just continuously decrease as you increase temperature. And then also the simple fluids tend to have a viscous response that is not dependent on shear rate or it's Newtonian. Now, in the case of the simple systems, minimal data can explain the systems and characterize them very well. But when you start looking at complex fluids, what we call complex fluids, then you can see significant deviations from these simple behaviors. And that is because as you change parameters, in our case, the relevant parameters are temperature and shear rate. When you change these, you can significantly change what's happening on the microscopic scale or molecular level. So you can see changes in the size, shape, and how they interact. And then also, when you're changing shear rate, as you go from the equilibrium to non-equilibrium microstructure, you can see a change in the resistance of the fluid to the flow. So you can see non-Newtonian behavior. And so when you're dealing with complex systems, it's really to your advantage to do some more exploration and go beyond one measurement. So I just want to highlight, so we use our technology, the Vrock Technology, which stands for viscometer rheometer on a chip. And I want to go over a few, before we get into the data, I want to go over a few of the details about the technology because it has some significant advantages for the types of measurements that we're doing. So what we're combining is microfluidics and MEMS, or microelectromechanical systems. And the way our technology works is we control the flow rate, so it's a controlled rate measurement. So we're forcing fluid with a syringe pump through our microfluidic channel. And what we're measuring then from 4 pressure sensors embedded at the bottom of the channel is pressure drop across the flow channel as the fluid goes through. So we are controlling the flow rate, from which we can calculate the shear rate, and we're measuring the pressure, and from pressure drop across the flow channel, we can calculate shear stress. So as we just discussed, the viscosity then is defined as shear stress over shear rate. So that is how our technology works. And I'm going to go over some more of the details in a moment about why the nature of the enclosed flow channel and the microfluidics, or the small scale dimensions, are very helpful to a lot of our measurements that we're doing. So the system, we have multiple instruments that we incorporate the Vrock technology into, and what we use for our experiments here today is our automated system, which is our Vrock Initium. And I'm not going to go over every feature that it has, but I just want to again highlight the features that make the experiments that we're going to discuss easier and higher quality. So our automated system has what we refer to as a sample retrieval feature, and the benefit of this is that we're going to load a single volume of sample, and we're going to do all our testing on that volume. So that's beneficial for not only minimizing waste of the sample, but also we know the history of the sample. And it's that single volume that experiences all of the temperatures and all of the rates. Since I mentioned at the very beginning, at the onset, that temperature dependence is something that we're investigating. We have Peltier temperature control over a broad range from 4 to 70 C. And also, now I'm talking about specific experiments that we've done, but there's a variety of additional types of experiments that you can design in terms of looking at stability of samples, things of that sort. And so it's relevant, I feel, that I mention that because this is automated, you prepare your samples ahead of time and store them on the sample rack prior to them being loaded. And this sample rack also has a temperature control system. So you can store them if you need to at temperatures close to refrigeration, or if you want to do some sort of accelerated stability studies, you can keep them warm and measure them as a function of time. So that's another relevant feature. And we have the ability to do shear rate and temperature sweeps. Again, because it's using our sample retrieval, we're using it on the same volume. And then I'll highlight the benefit of this a little more, but our software has some advanced measurement and cleaning protocols that make doing these experiments, it facilitates these types of experiments. So just to then emphasize some of these points a little more, some of the advantages. So I had mentioned that we use microfluidics. And in addition to the micron scale dimensions on our flow channel, in addition to that meaning that we use a very small volume, microliters, it also means that when we operate at high shear rates, we're not concerned about turbulence or secondary flows. So the Reynolds number, which is going to dictate when you transition from laminar to turbulence, is going to be proportional to the characteristic length scale of your flow channel. And because we're looking at microfluidics, when we go, as you'll see, some of our data is taken at shear rates above 100,000 reciprocal seconds. We have no concerns about any sort of hydrodynamic instabilities because of the microfluidics. Secondly, because we have the flow-through channel design, and our automated system is such that once the sample is prepped ahead of time in the vial, it's no longer going to be exposed to the environment. So we're eliminating the presence of any air-fluid interface. And first off, the reason this is beneficial is when we're doing these temperature sweeps and we're going up to 70 degrees C, we don't have to worry about evaporation. Whereas if you had a system that had the exposed sample, even when you try to maintain the environment, evaporation becomes a problem at elevated temperatures, but that's not a concern here. And also, one of the systems that we're going to be talking about will involve protein samples. And it's known that proteins, because some of the individual amino acid groups can have hydrophobic domains, they can migrate to the interface. And they can migrate to such an extent that you start having in traditional rotational instruments, for example, where you do have the air fluid interface, you can set up basically a locally higher concentration at the interface, and you have an interfacial viscosity contribution. But that won't be a problem here because we don't have that interface. And then the flow through channel design allows us to do the sample retrieval. So on this one single volume, we're going to be able to generate a lot of information. And specifically on that one volume, we're going to be able to put it through all of the temperature sweeps and then all of the rate sweeps. And we're going to know what the history of that sample has been. And then the other advantages, so some of the systems we're going to talk about, we don't really know, because they're complex systems, we don't know ahead of time how they're going to behave. And so our advanced software has the feature to operate in what we refer to as automatic mode. So what it will do is, as the sample is loaded and then as it goes through these changes in temperatures and rates, it will basically scope out the situation and adjust the flow rate so that we're not going to overpressure or be too low in pressure so that we're just getting noise. So it basically does the initial work for us. And then once we get some information in the automatic mode and we understand the sample, we can go back in and start getting more detail in the way that we want. Okay, so with that in mind, we're going to talk about the types of systems that we've looked at using our automated instrument. And we're highlighting the idea that these are complex fluids and they're going to behave in ways sort of unexpected. And if you tried to analyze these just using a single temperature or a single shear rate, you would miss a lot of information and you could be misled when you're trying to understand what's happening or apply them for a specific purpose. So what we're going to look at first, we have considering, so a popular topic are the stability of proteins and at what temperature will your protein denature. So we're going to look at how viscosity could possibly be an alternative method to monitoring this process in the proteins. Also, there's common pharmaceutical excipients that are referred to as thermo-reversible or thermosensitive. We're going to look at how these behave, what types of viscosity behavior we get as a function of the type, also the concentration, and we're going to see what the shear temperature and shear rate dependence is. And then we're going to look at how, when you're looking at applying, looking at the application of your fully formulated product, we're going to see, for the example of eye drops or ophthalmic formulations, we're going to look at the actual application situation so that you can learn how to evaluate that and design a relevant experiment, and then translate that into relevant shear rate and temperature dependent measurements. So again, in this case, we're going to pick something that basically a single point would not be enough to guide you when you're formulating. So the first case study that we're going to look at, as I mentioned, is looking at the proteins and the temperature dependence. So what we have here is we have a dilute bovine serum albumin formulation in a histidine buffer, and we're operating at about 30 milligrams per milliliter, so this is quite dilute. And what we're looking for here is we're measuring viscosity as a function of temperature. And as I mentioned at the beginning, when we were talking about viscosity reflecting what's happening on the microscopic level, you can imagine that as the protein denatures and it unfolds and then potentially associates with its neighbors, these changes in the microscopic behavior could then translate into changes in the viscosity. So that's why we're looking at this as a means of detecting this loss of the higher order structure and considering it as an alternative to other methods. And this one, as I mentioned before, is going to avoid the interfacial artifacts. And just to highlight how these artifacts can occur even in something so dilute, I've included a picture here at the top of the page where this is the 30 milligrams per milliliter sample, which we had in a vial and heated up in basically just a water bath. And what happened was although the bulk of it remained fluid and did not gel because the concentration was so low, we still saw gelling the gel ring at where the interface existed, because you have this migration of the sample that becomes locally concentrated high enough to gel. And so we avoid that in our enclosed system, which you could not in something like a rotational instrument. So just pointing out some of the advantages there. So now the data, if we look at the viscosity versus temperature, so the red curve here represents our protein formulation, and then as a reference, we have our buffer formulation. And the buffer, as we mentioned, is what we would consider a simple fluid, and it just behaves as we would expect. The viscosity continuously decreases as a function of temperature following the Arrhenius type behavior. And although the protein solution initially tracks the behavior of the buffer, at some point there's a dramatic upturn in the vicinity of 60 C, where the viscosity just starts going up very rapidly. So this alone could be enough and enough for you to believe that you're monitoring the process as the protein denatures. But if viscosity is convenient in the sense that we can do some more analysis and extract some properties related to the microscopic scale. So by that, I'm referring to the intrinsic viscosity, and from that, getting the hydrodynamic radius. So just to remind you what the intrinsic viscosity is and how that can relate to the hydrodynamic radius, before we do the analysis, I've included a little extra background here. So the intrinsic viscosity is just, if you're considering dilute formulations, which as I mentioned is what we're looking at here, and you do an expansion of the viscosity in terms of concentration, the intrinsic viscosity is just the coefficient to the first order parameter. So in the first order, what this is characterizing are the individual molecules. So that's mainly going to reflect size and shape. And we can relate this intrinsic viscosity, we can use it to calculate hydrodynamic size. And I won't go through the entire derivation, but determining the relation for the hydrodynamic size just comes from equating the viscosity expansion in terms of effective volume fraction. So the two first order terms have to be equivalent, and that allows you to estimate what an effective hydrodynamic size would be. And if you know the molecular weight of your molecules and the Avogadro's constant, determining the intrinsic viscosity from a viscosity measurement then can let you estimate this. Okay, so if we take our data and first we rescale the data such that we're looking at relative viscosity. So now we've taken the viscosity of our protein and just divided it by our buffer viscosity, and that gives us the green curve. And we see that when we look at this as a function of temperature, it's fairly flat until, again, we're approaching 60 C, and then it rises up. And it's using this relative viscosity that allows us to then estimate the intrinsic viscosity. So although in theory the full intrinsic viscosity analysis is more involved, there are single point approximations. So we can use that relative viscosity and the concentration of our sample to get this single point estimate. And from that, we can, knowing in this case we have the BSA, we know the molecular weight and the Avogadro's constant, we can estimate the hydrodynamic size. And then we are effectively monitoring that as a function of temperature. So again, we can see that this rapid rise that occurs between 60 and 70 is going to be consistent with the idea that the protein is unfolding and then potentially associating with its neighbors. So if viscosity is a convenient way of conveying the message, that's fine, but then also you can convert this to a size estimate, and it's an alternative to doing the light scattering measurement. Okay, moving on then to another system that is where temperature dependence is quite important. So a common excipient added to pharmaceutical formulations are the poloxamer type materials. And these are considered thermosensitive, thermo-reversible, different terms are used for them. And what they are, we'll just sort of outline what they are first before we go into the data that we've collected on these. These are what they refer to as amphiphilic triblock copolymers. So triblock meaning that you have three distinct blocks. Copolymer meaning you have two different types of monomers. And then amphiphilic comes from the specific types of monomers that we have in each block. So in this case, an amphiphilic is just meaning that you have basically dual type behavior. And our mid block in this case, the polypropylene oxide is more hydrophobic than the N blocks, the polyethylene oxide, because of the presence of this extra methyl group. And because we have this difference in hydrophobicity of the different blocks, these polymers can form, they can self-assemble and form different types of microstructures that are going to depend on not only the length of each block, but also then on the temperature and concentration. And this is a reversible process. So when you, for example, if you heat it up, then you cool it down, it should, in theory, go back to the same original state. And for one of the particular blocks that, or types of polymers that we're going to discuss with a particular A to B ratio, it's been established that what they start off obviously at lower concentrations or lower temperatures as individual polymers, but then as you heat or increase concentration, they will form spherical micelles. So what will happen in an aqueous environment, this more hydrophobic mid-block will associate with mid-blocks of other molecules and form the spherical micelles. So in the in-between stages, you'll have a mixture of individual polymers and micelles, but then ultimately, as you go high enough in either temperature or concentration, you'll have a system fully composed of the micelles. So this type of complex system, it's important to understand what the temperature dependence is. Specific applications for these are used as rheology or viscosity modifiers because they associate under specific conditions, then you can manipulate the behavior of your formulation. Also, given the fact that you have the mid-block, which is more hydrophobic, it can act as a solubilizer for certain active compounds that are less hydrophilic. And then because it tends to enhance the viscosity, they also can be used to minimize or slow down the sedimentation process. So there are a lot of applications for these types of systems. So the first thing that we were going to present here, we're going to look at how the type of poloxamer, and by type I mean the relative block lengths, so the A to B ratio, and the concentration is going to impact the rheology measurement. So what we're looking at is the relative viscosity as a function of temperature. So relative viscosity is just the viscosity of our solution divided by the viscosity of our solvent. In this case, it's deionized water as a function of temperature. So we've taken out the impact of change in viscosity of the solvent, and now we're just highlighting the effect of the polymer in this case. And we have two different poloxamer types. And again, these are just different A to B block ratios and different molecular weights. And for each type, we have varying concentration. So first off, what we can see is that unlike, say, the simple buffer solution that we looked at a moment ago when we were talking about the protein and the denaturing process of the proteins, this process is not a simple Arrhenius behavior either. So what we're seeing is the impact of this self-assembly and then changing in the structure as we change the temperature. And what we have on both of these plots, as you can see, it's a little hard to see on some of them, but there are actually two curves. So what we did was a forward and reverse temperature sweep so that we could essentially confirm the reversibility of this behavior. So we see that we're getting the complex behavior, and we're seeing that there's a very big difference depending on the type of poloxamer that we're working with. And then also it's quite sensitive to the concentration. So we can see that as we bump up concentration by just only 1%, we see the rise in the peak viscosity shifting quite a bit. And of course, when we're looking at the two different types, we're seeing a difference in the position of this peak. So with our one, it's in the vicinity of, say, 35 degrees C, whereas the other, it's closer to 65. So, and I'll just point out that just because it's sort of quite different from some of the other curves, when we're looking at our P407 sample at the 15% concentration, you see there's quite a bit of variability in the peak. And without going into too much detail, what's occurring here is we're basically looking at, with this increased temperature, we're not only just enhancing the viscosity, but we're generating something that is now exhibiting a yield stress. And so in this particular temperature range, the variability is coming from the fact that we're looking at the yielding process, which is not a steady state process. So in theory, then, you can use these viscosity measurements as a way of looking at the phase boundaries that exist between the fluid and gel state. And this is a particular example of how we could do this. Okay, so we see the general behavior of these systems. And I had mentioned before that one of the advantages of our software is that we can operate in automatic mode. So I had no idea ahead of time how these samples would behave exactly. So what we were allowed to do is use this mode, this feature, and it would then determine, it would scope out the situation and choose the appropriate shear rate for each temperature so that we didn't overload the system. But we haven't then fully explored the shear rate dependence that could exist at each temperature. So this is a good overview, and we see in general how things behave. But now we can go a little deeper and do a more thorough analysis. So what we're going to do is we're going to pick one of these curves, and we're going to look at the shear rate dependence as a function of temperature. So I picked one of the concentrations of the P407 sample, and so I'm just reproducing the curve on its own here, relative viscosity versus temperature. And we're going to look at the individual, we're going to look at these temperatures that we've labeled and do rate sweeps at these temperatures. So we're looking at 20, 25, 30, 45, and 70 C. And so as we move on to the plot to the right, we did the shear rate sweeps at these specific temperatures. And what we see is that as we go from low temperature to high, so 20 to 70, the material starts off as a Newtonian fluid at 20 degrees C, and then becomes non-Newtonian, increasingly so, and then this behavior starts to reverse, and we go back to something that's Newtonian at 70 C. And the other feature to point out is that looking at the relative viscosity versus shear rate, as we go up to the highest shear rate, so now we have data up to about 100,000 reciprocal seconds, we see that these curves are starting to merge. And so what's happening then is if you're introducing these excipients into your formulation with the intent of enhancing viscosity, you're going to lose this viscosity enhancement as you increase to this highest shear rate. It still exists to some extent, but it's not as dramatic as if you're operating at something low. So to highlight this a little more, we've sort of eliminated the rate sweeps and gone back to just relative viscosity as a function of temperature. And now we're looking at our original curve, which is in the red, where we operated at an automatic mode. And so in this case, it was adjusting the shear rate for each temperature. But when we take the information that we got from the shear rate sweeps and incorporate it here, what we're seeing as the viscosity enhancement that we get with temperature increase is shear rate dependent. So we can see what happens in the zero shear limit. So that's basically extracting the plateau value from the curves we just looked at. And as we increase the shear rate to say 30, 60, or 100,000 inverse seconds, we see that the peak is dropping. So if your intent is to enhance viscosity at say 30 degrees C, you need to really consider what is the shear rate in your application, because the degree of enhancement will be highly dependent on the shear rate. Lower shear rates, the more enhancement you'll get for this particular system. So it's just emphasizing that when you're doing these measurements of the systems where temperature is very important and shear rate is very important, you want to consider how that will correlate to your application so that you're really formulating in the appropriate way to get the benefit that you want. Okay. So our final system that we're going to look at, and this is, now we're looking, so we've addressed sort of understanding the proteins and how their stability is with temperature, excipients, Now we're looking at a fully formulated system, and these are going to be the eye drops formulated for dry eye relief. And we're going to look at these, and we're going to think about what type of measurement would we want to do on the eye drops that would be relevant to the actual application process. So again, we're doing this so that we're emphasizing that, when you look at the application, a measurement at a single temperature or a single shear rate might not reflect what's really happening for your application. So what we have here, just to show you that even though the application is complex and the ocular environment is complex, you can often simplify things to get some idea of what relevant shear rates are for your application. So what we have on the left here, they've actually measured it's basically a camera, the eyelid motion throughout the blink cycle. So the relevant one here for our particular case of estimating the shear rate is to look at the velocity as a function of time. And so this first peak is the eye closing and then opening again. So we're looking through the full blink cycle. So we start with the eye open, the eye closes, and then opens again. And so what we're seeing is the velocity goes from essentially at the turnaround point 0 to some maximum value, which is going to depend on the specific blink, and then also it has a person-to-person variability. And the way we can translate the viscosity of the eyelid to a shear rate is to consider simplifying the system. So on the right here, we've taken the system where we're looking at the fluid between, say, the eyelid and the cornea, the stationary eye surface. And we're considering we can use the velocity as we discussed at the very beginning on, when we defined what is viscosity. We know that we can calculate the shear rate across a gap of fluid by looking at the velocity divided by the gap thickness. And so to get sort of a range, a ballpark range of what shear rates would be relevant during the blink cycle, we can use the range in velocities that we have from the actual measurement of the blink, and then also some estimates on the tear film thickness. Now, the tear film thickness ranges are quite broad, so ranging from 3 to 40 microns. But using these numbers, we can basically get what would be sort of the minimum maximum shear rate and then the maximum potential shear rate that we could get. So we're going to, obviously we said that in the turnaround points we have 0 velocity, so that would be, we want to go as low as we can go to see what happens there. But then in terms of the maximum rate, it's going to be anywhere from, say, 4,000 to 100,000, so very broad range. So this is just a way to take a complex system and try to break it down into fluid flow between a gap using parameters that are available so that you can estimate what kind of range you want to measure in. So when we look at an example eye drop formulation, now we're going to see, can we then measure in the shear rate range, and what can we learn from this? So in this case, we have the viscosity versus shear rate. And we've also included the idea that we know that the eye temperature is going to be warmer than room temperature. So the other factor here is not only is shear rate important, but what happens as a function of temperature. So you have your eye drop formulation, which is quite likely at room temperature, and then when you put it on the eye, the temperature will increase to something close to body temperature, so somewhere around 37 C. So to really fully characterize an eye drop for your application, you would want to do a rate sweep as low as possible, and then preferably up to something in the vicinity of 100,000 reciprocal seconds. And then also consider how your formulation will change as you change the temperature. And in this case, we didn't quite get to the 0 shear plateau, which would be of interest based on the turnaround points in the blink cycle. But it fits very nicely one of the common shear thinning models so that we can estimate that from our data. So we can see how shear rate impacts the viscosity, and then also how temperature impacts the viscosity. And then this can be used when you're formulating, if you have a particular type of profile, that shear thinning profile you want, or maximum plateau viscosity that you might want as well. So just an example of where the application, knowing rate dependence and temperature dependence is important. Okay, so to summarize up then, after we've sort of gone through these different case studies, viscosity is really more than just one number under one set of conditions. And to fully utilize the viscosity measurements and turn it into a powerful tool, you really need to explore the different parameter space. So it can help in many situations. So one of these being, if you need to correlate your testing conditions to performance, use it as a predictive tool. And so that example was when we were looking at the eye drop solution and how it could behave in the ocular environment. Again, important to know temperature dependence and shear rate dependence. And then also in just the formulation process, if you're looking to develop an investigative tool to guide you in the formulation process, you can use viscosity to probe how interactions in microstructure are changing and what's occurring there. So in this case, we looked at the self-assembly of the polymeric excipients that are temperature sensitive, and then also looking at the stability or denaturing process of proteins with temperature. Okay, so we'll stop there and we'll check to see if we have any questions. And it looks like we don't. So I want to thank you for attending. And if I think that we send out the webinar to everyone who's signed up. And so if you have follow-up questions, you can contact us that way.
We'll stay on for about 2 more minutes. If you want to submit a question now, just go to your GoToWebinar control tab and go ahead and submit the question. Any questions that cannot be answered will be followed up directly through a separate email, and we'll be happy to help.
Okay, so we have 2 questions that have come in. So first off, one of our attendees is asking if I can go over the slide that is talking about the hydrodynamic size. And so, yes, we can go ahead and go over that. Okay, so yes, we can go ahead and take a look at that again, and I'll go into some more detail. So we'll start with this one here, where we're talking about the intrinsic viscosity and the hydrodynamic size. So one of the benefits of doing the intrinsic viscosity analysis is that you can use that value to estimate hydrodynamic size. And the relationship that is derived really just comes from doing the series expansion of the viscosity in both concentration and effective volume fraction. And although we weren't doing the full intrinsic viscosity analysis, we were doing a single point estimation. The idea for the full analysis is that you would do a dilute concentration series to get this intrinsic viscosity. And so the intrinsic viscosity being the first order coefficient, the coefficient to the first order term, that's indicative of just individual molecular behavior, because at such low concentrations, these molecules are very far separated. And so that's the general idea behind why the intrinsic viscosity could relate to the hydrodynamic size. But then the actual process of deriving the equation is really just equating these first order terms in the 2 expansions. So whether you expand in terms of concentration or effective volume fraction, those terms should be equal. And so it's from the effective volume fraction that we get basically a hydrodynamic size of the molecule. So just rearranging the parameters, that's how we calculate that. If you contact us directly, we can give you some more information on the specifics of that derivation, but that's the general idea. Okay, so hopefully that helped. And again, if that wasn't clear, let us know and we'll contact you directly. Okay, so the second question that we had was whether we have examples of using our viscosity measurements to study and understand protein-protein interactions. And yes, we do. So we sort of considered that a separate topic. So what we've done with looking at protein-protein interactions, since we're on the topic of intrinsic viscosity and hydrodynamic size, we've done experiments on proteins in different buffer formulations to do an intrinsic viscosity analysis and look at how both the intrinsic viscosity and then the Huggins parameter, which then is characteristic of how these proteins are interacting. So we've done intrinsic viscosity measurements on protein systems using those parameters to understand. And then, of course, we've done measurements on higher concentration systems just to look how the overall viscosity will vary. And the systems we've looked at are looking at the common additives that you would incorporate into your buffers formulation. So different types of sugars, some of the individual amino acids such as arginine or histidine hydrochloride, urea, which is expected to be another way of causing the protein to denature. So we have looked at different buffer systems to see how changing those would then change how the proteins interact and how that reflects in the viscosity, both in the dilute case to estimate the different parameters and in the concentrated regime. So hopefully that but we didn't really present that here. That's a little bit separate topic. Okay. Okay, so I think those, oh no, we just had one more. So we had one more question where they're asking, can we use our extensional flow channel on the initium? And at this time, we don't have that option available. Right now, we can only use our extensional chip on our Vrock system. So it's the manually operated system. So at the moment, no, we don't have that option available. Okay, so thank you everyone for joining us. And as I mentioned, if you review the presentation or a question comes to you later, please contact us directly and then we'll give you an individual answer in response to your question. So again, thank you and have a good day.